Welcome back to this next video in which we are discussing topological homeomorphisms. Okay, so in the previous video what we saw is that if two topological spaces are homeomorphic, then what that actually means is that the two topological spaces are actually identical to one another, up to the fact that you've used different symbols to denote the elements of the two different topological spaces potentially. Okay, but as far as the actual mathematical structure that we're interested in is concerned, they are utterly identical. Okay, so in the previous video then we saw the formal definition of how you check that two topological spaces are homeomorphic. You have to find a topological homeomorphism between them, one of these relabeling maps, so a bijective map from one of the topological spaces to the other, which then also forms this very natural bijective correspondence between the subsets in the topology of the domain topological space and the subsets in the topology of the codomain topological space. What I want to turn my attention onto in this video is exploring more intuitively what does it mean for two topological spaces to be homeomorphic? What does it mean for two of them to be the same? Okay, and what we're going to do for this is we're going to go away from this very simple example here to a much more complicated but much more intuitive topological space, i.e. real topological spaces in the real world. Okay, and I'm going to show you what I think is an extremely interesting result first, and then this will allow us to get intuition for what it actually means for these topological spaces to be homeomorphic, and it's really beautiful and really interesting, this. Okay, and this starts to capture the true core of what the subject of topology is all about. Okay, so firstly then, let me just remind you of the two-dimensional plane and how the two-dimensional plane can be considered a topological space. Okay, so by the two-dimensional plane then, I mean the set that goes on and on in two dimensions forever and ever and ever. Okay, so that's what I mean by the two-dimensional plane. Now, how can we consider this a topological space? Well, what we can do is we can put all of the points, we can represent all of the points in the two-dimensional plane by a symbol that we'll put in a great big set, which I'll call X here. Okay, so we'll put all of these together in a great big set, etc. And what we're going to do is we're going to define a topology on this so that it mirrors the topological structure of the two-dimensional plane here. Okay, so this is where we need to remind ourselves of intuitively what is a topological structure on a set actually trying to capture. So we discussed this in the earlier video in this playlist on topology entitled Topological Spaces. The informal intuition that you should have for what defining a topology on a set actually does is that it allows you to state which points in a set are next to each other. Okay, it gives a set a notion of which points in that set are next to each other and which are further away from each other. Okay, now clearly this set of points on the two-dimensional plane, this does have a notion of which points are next to each other and which are not. Okay, and by equipping this set with an abstract topology, we can capture that same structure. Okay, now remember, the way that you actually go from having just this topology, which is this set of subsets of the set, to actually being able to decide which points in the set are next to each other is informally, it is that you look and see which points in the set are always found together in all open sets where they appear in the topology. Okay, so informally what we want to do on this set is we want to draw little lines in between the points in the set that are next to each other. Okay, and the way we'll decide whether we want to draw a line in between two points in this set is, do they always have to occur together whenever one of them appears in a subset that's in the topology? And if they do always have to appear together, then we're going to say that they're next to each other. So if it's always the case that when one appears, the other has to appear there as well in any of the open sets that are in the topology, then we'll say that they are next to each other. Okay, so that, remember, is the informal intuition for why this set of subsets of a set can capture this concept of which elements of the set are actually next to each other. Okay, so just to remind you then of the intuitive view of the topological structure of the plane then. Intuitively, the topological structure of this looks like a great big lattice, okay? And let me explain how. If you imagine zooming in on this plane, zoom in and in and in and in and in to an infinitesimal scale, so zoom in further than you can ever zoom in, okay, then what you can imagine informally, this is the informal intuition, what you can imagine is that if you zoomed in far enough down to the infinitesimal scale, you would see the plane stitched together like so, okay, you'd see a lattice like so. And let's say this is our point P here, so I'll colour it in. So here's our point P in the plane, and now we've zoomed into this infinitesimal scale, and here you can see that it's connected to a few points here by these lines. So here's a point it's connected to, here's a point it's connected to, here and here. Okay, so it's connected to these points which are infinitesimally close to it. Okay, and this then is the topological structure of the plane, this very ordered and beautiful lattice. Okay, that's the informal intuition for the topological structure of the two-dimensional plane. Okay, and we can capture this concept by putting a topology on this set here. Okay, now more normally, the way that we capture abstractly this structure of the plane, the topological structure of the plane, is we create the set R2 and we then imbue this with standard topology, and that then captures this concept. Okay, because remember those sets that don't contain their boundary, if you want to ask which points around P are always going to be in any of those sets, i.e. which points are going to be next to it, then you can always make those sets that are around P with no boundary as small as you like, and therefore all the points aren't going to satisfy the condition to be next to P, but except those that are infinitesimally close to it, those that are so close that you can never get a little open set around the point P that doesn't contain them. Okay, now of course, formally that doesn't exist, that doesn't mean anything, but intuitively that's the intuition for why the standard topology on R2 actually captures this topological structure, this informal intuition for the topological structure of R2. Okay, so there's just a reminder of the informal intuition about what the topology on R2 actually looks like. Okay, and we're going to use this to get an understanding of what this plane is actually homeomorphic to. Okay, so here is a nice result. What I can do is take a little subset of the plane here that doesn't contain its boundary, so it's going to be one of these subsets that doesn't contain its boundary. Okay, so it's all the points inside here, inside this dashed line that I've got here, and I'll colour those in. So all the points that are inside this dashed line, which I'm now colouring in yellow, I'm going to define that to be this set. Okay, and I'm going to have this set with the exact same topological structure that it would inherit from the larger plane. Okay, so again, if I zoom in infinitesimally, I'd see something like this. Now, I claim that this is actually topologically homeomorphic to the entire infinite great big two-dimensional plane, and I, for one, find this very, very deep. Okay, because how can this, which we can finitely write down there, actually be homeomorphic to something that spans on and on forever? Okay, well, let's think about this. When we actually look at the informal intuition for what the topological structure of these two things looks like, this is the same picture. Okay, so they look like the same lattice, so it's looking very good. And what's the other property then of the infinite two-dimensional plane? It just looks like this forever and ever and ever. And the other important property that it has is that you can never ever get to the end of it. You can always go on and on forever, and you will never get to the end of it. Now, I claim that you can never ever get to the end of this either. And you might think, rubbish, I can see the end of that here. But imagine that you are actually existing in the yellow world here, in this two-dimensional yellow world, this two-dimensional topological space here. Okay, you cannot see this hashed line that I've got here. Okay, that's not in your world. You're not allowed to see that. You can't see it. It's not in your universe. Okay, so all you can see is the yellow points. Now let's say you try to approach the edge of your universe. Okay, so let's say you got very, very close to it from our advantaged godly view that we can see this universe. You're very, very close to the edge of the universe. Let's think about it from the perspective of the little person in the two-dimensional world though. Okay, can he ever actually get to the edge? Well, he can't get to the edge because the edge doesn't exist in his universe. Okay, and moreover, he can always get closer and closer to the edge from our godly perspective. He can always continue going on, because wherever he is, I can always get him closer to the edge. So he will never ever stop going on. He can go on and on, approaching the edge of the universe forever. He can always get closer and closer and closer to it, but he will never actually get to it because that doesn't exist in his universe. Although we can see it from our advantaged position, as far as he's concerned, that doesn't exist, so he can't actually get to it. Okay, but he can always get closer and closer and closer to it. He can always go on and on and on. As far as he's concerned, that universe goes on and on and on forever. Would this little two-dimensional man be able to tell that he was in this little set here compared to the infinite two-dimensional plane? The answer is no. There's nothing he could do, absolutely nothing he could do to distinguish between this one, this topological space, and the entire two-dimensional plane. Because as I say, as he approaches on and on towards the edge of the universe, he'll just go on and on, just as he would if he was in the infinite two-dimensional plane. Okay, so in fact, this one is absolutely topologically identical to the entire two-dimensional plane. The topological properties, which points are connected to which, is exactly identical. Now, you could come up with a function, a topological homeomorphism, which maps all of the points here to the infinite two-dimensional plane. I'm not going to do that because it takes ages to actually make this rigorous and turn it into rigorous expressions for the functions, but I hope you can intuitively imagine that I could blow this up, stretch this out, infinitely, and turn it into the two-dimensional plane and not actually change the topological structure at all. And the way that you should be viewing this is the intuitive view of the topological structure in terms of which points are connected, are next to, are close to other points. Okay, when you stretch this out, imagine it's made of elastic and you stretch it out, you don't actually change the topological structure of it at all. The points that were next to each other before you stretched it out are still next to each other afterwards. Okay, you've changed the distance structure on it, you've changed the metrical structure on the piece of elastic, but I'm not interested in metric spaces. We're not studying metric spaces, we are studying topology, not metrics. Okay, so as far as the topology is concerned, stretching out the piece of elastic has absolutely no effect. Okay, and that actually gives us a very nice way of intuitively understanding whether two real topological spaces are homeomorphic. If you imagine that the space is made of elastic, then you are allowed to stretch the elastic to your heart's content, and that will not change the topological structure. So stretch the elastic to your heart's content and turn it into whatever shape you like. Okay, as long as you don't ever tear the elastic or forge the elastic, melt it and stick it together somewhere, that's not allowed. But as long as you're just stretching it, then that's fine. You don't change the topological structure at all, and your two spaces will be homeomorphic before and after. Okay, so that, I find, a very deep result, that this, what looks to be a finite, bounded structure here, is actually topologically homeomorphic to the entire infinite two-dimensional plane. And it's really got to do with the fact that the infinitesimal here is just as perplexing as infinity out there. Okay, so the infinitesimal nature of this, that you can always get closer and closer and closer and closer and closer to the boundary but never get there, is capturing the exact same perplexing property of the fact that you can go on and on for infinity. It's the exact same thing. Okay, so that's the first intuitive topological homeomorphism that I want to tell you about. And as I say, you could make this all rigorous. You could find topological homeomorphisms functions. You could rigorously express them and prove that it satisfies this condition of being bicontinuous. But I hope that the intuition is more interesting and more powerful in a way than actually doing those exercises. Okay, so more topological homeomorphisms. I absolutely love this because it's all visualization and you don't actually have to do any abstract equations. Okay, so another one then. What I want to show you is that the sphere, the two-dimensional surface of a sphere, is topologically homeomorphic to a cube. Geometrically, they're completely different. Okay, the metrical properties are not the same at all. Metrics are stronger than topologies. Topology can be stretched. Geometry can't be stretched. If you stretch a piece of elastic, you completely change the geometry of it, whereas the topology doesn't change at all. Topology captures a more weaker part of geometry, a more foundational part of geometry than metrics do. Okay, so let me draw a picture then of a sphere. Okay, so here is going to be a sphere embedded in R3 here, we can initially imagine. Okay, so here it is, so like the surface of the Earth, and I'm just viewing this as the surface of the sphere. I'm not viewing it as the three-dimensional, actual bits inside. I just want the surface of the sphere. And I claim that this is topologically homeomorphic to the surface of a cube here. Okay, so again, this is not the actual three-dimensional bulk of the cube, I just want the surface of the cube. Okay, now why is that going to be the case? Well, again, all we need to understand here is stretching elastic. Can you understand that if this ball here was made out of elastic, so imagine it's a very nice stretchy material, that I could stretch it and stretch it and stretch it and turn it into the surface of the cube there very easily without actually ever tearing it at all. Okay, yes, I make it much more, much less curvaceous, much more hard corners and things like that. But I have never actually had to break the elastic to turn that into that. All I've done is sort of pull it a little bit, stretch it a little bit, and we know that that's not going to change the topological structure on here at all. It's not going to change how points are actually connected to each other on the sphere. The same points that are connected to each other here are also connected to each other here, so they're topologically identical. They're topologically homeomorphic. And I hope you can appreciate that the sphere is not topologically homeomorphic to the two-dimensional plane. These two are fundamentally different topological spaces. The way they are connected together, the way the points of the sphere are connected together is different from here. Okay? If I was a little man living in the sphere on the surface of the Earth, I could work out that I was on the surface of the Earth. Okay? Because look, in the sphere, if you go on walking and walk, in the two-dimensional plane, if you walk and walk and walk and walk, will go on and on forever, whereas in the sphere, eventually you'll come back to where you are. Okay, so I hope intuitively you can see that that is folded up on itself in a way that is very different from here. The way that the points are connected to each other here on the global scale is very different from the way that the points are connected to each other here on the global scale. Okay, so intuitively, even if not rigorously, I hope you can understand that those two are not going to be topologically homeomorphic. Okay, right, but the sphere and the cube, the surface of the sphere and the surface of the cube, are indeed topologically homeomorphic. And to end this video on topological homeomorphisms, what I want to give is one of people's most famous examples, that the torus, a donut, the surface of the donut, is topologically homeomorphic to the surface of a teacup. Okay, so let me try and explain this, and again we'll do it just through stretching. We'll imagine elastic, and we're stretching elastic. Okay, so let me draw a picture of a torus. So a torus is just the fancy name for a donut, so I'll write it out here, torus. Okay, and people usually draw it like this. Okay, so here it is. It's just the surface of a donut. So an American donut. In England, they don't look like this, but an American donut, in America, they have a hole in them. Okay, so it's like one of those hoops that you can throw into a swimming pool and then you dive down to the bottom to grab it. One of those, but we just want the surface of that. Okay, we want the surface of a torus. Okay, now this is another different two-dimensional topological space from the two-dimensional plane and the surface of the sphere here. Okay, this, again, you'd be able to tell the difference if you were living on here from the sphere and the plane here. Okay, so this is fundamentally different from this one. I can't stretch this in any way to turn it into the sphere, and I can't stretch it in any way to turn it into this. These are fundamentally different, and I can't turn the sphere into this one either just by stretching it, because I can't get this hole in the middle. What I'd have to do is puncture the sphere on two sides and then glue it back together, and that's not allowed. That's not stretching. As soon as you've punctured and glued things in different places, you are changing which points are fundamentally connected to other points. Okay, you are changing the topological structure. So this is different from these two here. I can't turn these two into this just by stretching. Okay, but I can turn this into a teacup, something that resembles the surface of a teacup. And let me show you how. So what I'm going to do is I'm going to stretch this side here. So imagine it's made up of elastic, and I'm going to stretch this side out. So I'm going to do this in two steps. So firstly, the first step I'm going to end up with is something that looks a little bit more square, because it's easier to draw if it's squarer. Okay, and it's going to look now like this. Okay, and it will have its hole through here. And how can I make that look a little bit better? I'll sort of put lines in like that. Okay, so it's still got a hole in there, and it's still just the two-dimensional surface. So hopefully you can appreciate that all I've done is made it a bit squarer, put it on its side firstly, so I've moved it up on its side like this, made it a bit squarer, so got rid of the curves and made it square like so, and then pulled this side out a bit like there. Now, how can I turn that into a teacup? Well, now imagine just taking your thumb here. So imagine this is my thumb, and I'm now going to press down here and stretch the elastic in on itself here, like so. So I'm pressing my thumb into there and stretching the elastic down. Now, can you see that that actually looks reasonably like the surface of a teacup? Here is the handle that you will put your finger through, and here then is the cup where you can put the liquid. Okay, so just by stretching this surface, not by making any tears, not by gluing bits back together, okay, so purely by stretching, which preserves the topological structure, it preserves which points are connected to other points, I can turn the torus, this donut here, into the teacup. Okay, so indeed the surface of a donut is topologically homeomorphic to the surface of a teacup. Their topological structure is identical. You might label up the points of a teacup differently than the points on a torus, but fundamentally, as far as topology is concerned, they are identical, and any theorems that you come up with about the torus's topology will also apply equally well to the surface of a teacup's topology. Okay, so we will end it there. I hope the concept of a topological homeomorphism is now firmly in your minds.